we present our paper, ABC Auxetics, an implicit design approach for negative Poisson's ratio materials. Typically, when we apply a tensile load on a block of material, the block shrinks in the transverse direction. However, there are special materials that expand in the transverse direction under tensile loads. Such materials are defined as auxetic, as they can be defined as having a negative Poisson's ratio. That is, the ratio of transverse contraction strain to longitudinal extension strain in the direction of the stretching force. While Poisson's ratio is defined as a property of bulk material, there is extensive research on using special types of geometric patterns to achieve auxetic behavior. The basic idea is to define a unit material that exhibits auxetic behavior, then pattern this cell in space to generate cellular structures. Changing the geometric pattern of the unit cell allows one to change the intensity of the auxetic behavior, as quantified by the Poisson's ratio. What is interesting is most of the currently known cellular auxetic structures belong to a select few categories of cellular geometries with fixed structural topology. The inspiration for our idea of ABC auxetics comes from the observation that one of the currently existing class of auxetic structures can be generated by creating carefully arranged cuts in a sheet of material. In this example, notice that these cuts are arranged according to the P4 wallpaper symmetry, with the translation cell containing 4 sequentially perpendicular cuts. While most current literature uses this in other wallpaper groups for such arrangements, we also notice that these arrangements can be alternatively interpreted as visual abstractions of two-dimensional weave patterns. In this specific example, the weave pattern is that of the commonly known plane weave. Our fundamental question in this work is, will other weaves also lead to auxetic behavior? Let's look at the procedure to generate ABC auxetics, but first we need to understand what the A, B, and C mean. Consider a two-way, two-fold weave, such as the one shown here. This is a special example known as a genus 1 fabric. An interesting property of such weaves is that they can be represented using 3 parameters, say A, B, and C. A is the number of up crossings, that is, the number of times the horizontal weft thread goes over the vertical warp thread, also known as up crossings. Similarly, B is the number of down crossings, that is, the number of crossings a horizontal weft thread goes under a vertical warp thread. Finally, C is the shift of this entire unit sequence of warp and weft threads in the next row. In this example, A, B, and C are 2, 3, and 2 respectively. Another way that this weave can be represented is as a matrix, where the color of a cell represents the direction of the thread. The first step in our method is to take this matrix and convert it into a set of line segments based on the number of contiguous warp and weft regions. By interpreting these line segments as cuts on a sheet, we can generate structures that are potentially auxetic. Given a set of cuts arranged according to a given weave pattern, the idea behind generating an auxetic structure is to imagine the cuts growing in space. Since our cuts are line segments, one can imagine the growing shapes as capsules. The interfacing boundaries between any 2 neighboring capsules gives us the structure. Computationally speaking, this is the equivalent to determining a Voronoi tessellation of space with line segments as the Voronoi sites. Therefore, for a given set of woven patterns, we first compute the Voronoi tessellation. Following this, we thicken the curved boundaries of the tessellation to obtain our structure. With this procedure, a wide range of structures can be generated. For example, the parameters 1, 1, 1 corresponds to the plane weave pattern. Notice how this pattern results in structure similar to the reentrant auxetic structure. Twill structures can also be generated with parameters 2, 2, 1. Many other interesting variations can also be used. While any values of A, B, and C can be used, for this work we limit A and B to be between 1 and 10, and C must be less than A plus B. Recall that our original question was, do weave-based cuts induce auxetic behavior in general? To investigate this, we conducted a systematic study of a wide range of structures to determine the relationship between the effective Poisson's ratio and the ABC parameters. Our study involved a combination of FEA analysis as well as mechanical testing of 3D printed samples of selected structures under tensile loading. Our analysis showed several interesting results. In cases where A, B, and C are equal, our FEA analysis showed highly negative Poisson's ratio, as can be seen here with these clips. Our mechanical tests showed similar qualitative trends as well. We also studied cases where we varied the parameters A and restrained B and C as unit constraints. We observed that, contrary to intuition, the structures, despite containing long horizontal elements, exhibited auxetic behavior. In fact, both FEA and mechanical tests showed a positive correlation between the parameter A and the intensity of auxetic behavior. Conversely, we also considered the cases where only the parameter B is varied. In this case, both the FEA and mechanical tests show a decrease in magnitude of the Poisson's ratio. While all our structures exhibited auxetic behavior regardless of the weave parameters, there is a much richer design space for structures with wider range of mechanical behaviors. Here are two examples for future research in this direction. First, the ABC parameterization is only a special case within the entire design space of two-way twofold weaves. Based on early works of Grunbaum and Shepard, weaves can be defined by using binary matrices as fundamental blocks, as shown in this example. The resulting structures show local auxetic behavior induced by the fundamental block. Understanding this design space is an exciting direction for future research. Second, the use of more complex Voronoi sites instead of lines may allow for an entirely new way of generating structures, with fine control of Poisson's ratio throughout the spatial domain. In summary, this work reveals a vast and uncharted design space for mechanical metamaterials. Thank you for watching. For more details on our results, please download our paper at midl.tamu.edu.